So I think we have to move on to the next speaker. Again, thank you again to our last speaker. Our next speaker is Wassim Haddad from Georgia Tech, talking about the role of thermodynamics in the control of large-scale dynamical systems and network systems.
Thank you, John.
Take it away, Wassim.
Can everybody hear me?
We can hear you.
Excellent. So I want to talk a little bit about thermodynamics, but from a different perspective, in particular from a dynamical systems approach, and how to control systems in more so large-scale networks. So just let me give you a little bit of an outline here. So I'm going to predominantly concentrate on aerospace systems because that's what my background is. I'm going to talk about energy and entropy-based control, and in particular hybrid control, and I'll define what I mean by that. That's going to be characterized by impulsive differential equations or impulsive dynamical systems. Talk a little bit of the different architectures, and I'll show you how the role of thermodynamic stabilization enters into this problem, so that when you get to close the loop on the system, you actually get a thermodynamically consistent closed loop system that quantifies energy and entropy type ideas. Then I'm going to move over to network systems, which are extremely important. And I'm going to spend a little more time on the network. So the first part I'm just going to go through pretty fast, but show you how to design distributed consensus protocols with intermittent information between agents and how that works. So the motivation is in aerospace systems, we have very complex interconnected dynamical systems. They typically have a multi-echelon hierarchical structure. You can view basically the lower levels of the system as continuous time controllers. And as you go up the hierarchy, these become supervisory control or discrete event systems with an ultimate supervisor that actually switches between different controllers so that you can capture different modes of operation in the dynamical system. So you have switch systems, and this gives impulsive or hybrid dynamical systems where now you have discontinuous system motions. So you no longer have continuous dynamics on evolving on appropriate manifolds, but rather you have discontinuous dynamics, and they are actually left continuous. You also have decentralized architectures where basically you have different things like weight, size, power, cost considerations. You have different inputs and outputs, and you look at decentralized rather than a centralized architectural scheme for the problem. Now, when you actually look at the difference between dynamical systems in aerospace and thermodynamics, in aerospace systems, these systems are characterized by Newtonian mechanics, i.e. Lagrangian Hamiltonian dynamics. You can think of them as microscopic dynamical models versus in thermodynamics, you have a macroscopic model where you basically have heat flow in a particular direction, energy flow in a particular direction. So basically what's happening here is when you look at it from a microscopic dynamical point of view, that the microscopic details are actually obscured on the macroscopic level because you have heat flow. So that then the question becomes, you can actually view this as a measure, as the macroscopic model as an inherent model of uncertainty, especially as you add more and more dynamical modes to the system. So then the question becomes, how can we use thermodynamics not only to model, but more importantly, to control these large-scale dynamical systems? Can you do that? Can you actually convert the system from looking microscopically, wherein Newtonian mechanics basically has the rule, if you will, versus looking at it from a macroscopic point of view, where you're looking at it from a thermodynamic point of view? One way to do that is basically design one-way energy flow resetting controllers. So you can think of a continuous motion for the system plus a discontinuous controller. Together, when you close that loop, the system starts acting as if it's a diffusion system, or it's a diffusive system. So that will give you the thermodynamic stabilization approach for large-scale systems. So in order to do this, one has to look at thermodynamics from a dynamical systems perspective, from a basically dynamical modeling system perspective. Now that prompted me back in 2005 to actually look at a system theoretic approach to thermodynamics and capture the conservation of energy laws, the non-conservation of entropy law, from a systems perspective point of view, from basically a dynamical systems perspective point of view, where basically you have the absence, if you will, of Poincare recurrence, because in mechanical systems you have always this Poincare recurrence for lossless dynamical systems. But in thermodynamic systems and isolated systems, you have the emergence of damping, if you will, is indeed ubiquitous. So you need a systems foundation to be able to do this, to capture things like finite time thermodynamics, stochastic thermodynamics, systems with delay, functional differential equations, and so on and so forth. So just to give you an idea of how this actually works, in high-level idea, you can look at this thermodynamic stabilization approach. You can look at the interaction between subsystems and subcontrollers, because you're looking at decentralized controllers, as a pair of interacting subsystems, and basically exploit the coupling between the physical plant and the energy-based controllers. So if the energy level of the plant is at a high energy level, and the energy level of the controller is at a low energy level, and if it's acting in a thermodynamic sense, then the energy from the plant is going to flow to the controller. And hence, what's going to happen is the energy of the plant is going to decrease while the energy of the controller is going to increase. Now, the energy of the plant is the physical energy, but the energy of the controller is actually emulated energy. But on the other hand, this emulated energy can go back to the plant through the actuators by looking at sensors and actuators to impart actual physical energy back to the plant. So the idea here is to design a controller that essentially affects a one-way energy flow and reset this so that you enforce the second law. So basically, you only have one directional energy flow. And you do this using a hybrid architecture for the controller, so you can capture things like multiple modes of operation, hierarchies in the architecture, and switching type dynamics in the system. So just to, without getting too much into the mathematics, this is what the model looks like. Basically, you have a state space model. It's an open system in a sense that you have an input, a state variable, and an output to the system. They evolve on different spaces, state spaces and dimensional, the input space, the output space, and these systems are all interconnected. So you can actually break down this vector Fi, this vector field, in terms of this dynamics where you have a coupling between all of the interconnected subsystems, and the coupling is actually, it couples the entire state of the system. So you have the subsystem dynamics that's given by Fi, you have the interconnection dynamics that's actually a function of the entire state of the system, and then you have the inputs and the output variables of the system. Now, the way we design the architecture for the controller is basically a hybrid controller. It is a dynamical system itself. So if you think of this as the plant, and then the subcontrollers, it's basically what I said, a decentralized controller, which essentially means that you have multiple hybrid processes operating each independently, which each of these G sub i's receives a subset of the available outputs, or rather measurements, and then has an update on a subset of the control inputs back into the system. And you have this kind of characterization of the dynamical model. Basically, you have a continuous dynamics that evolves between resetting events. Then at resetting events, you have a difference equation. And then you have a resetting set that captures the thermodynamic structure, which I'm going to say a few words about in a second. Now, without going into the technical details, because I'm going to go into this more so when I look at the network problem, let's concentrate on the resetting set, just what this thing looks like here and the figure that's associated with it. So we have the control energy, basically. If you look at the rate of change of the control energy is 0, and the energy in the controller is positive, then you reset. And in other words, this set here captures the set of all points in the closed loop state space that corresponds to decreasing controller energy or emulated energy. And notice that only the knowledge of the state of the controller and the actual physical measurement is sufficient to determine whether or not you reset or not. So if you view this as the plant energy, you view this as the controller energy, as the interchange energies between the plant and the controller. If the energy is positive to the controller, but it's actually at a maximum, then reset. And continue doing this until you actually get rid of all the energy in the plant. You could do something similar with an entropy problem. Let me skip this slide so I can go into the network problem. But just to give you an idea how that looks like when you look at and apply it on physical systems, we've applied this on several GE engines, and the one in particular that I'm going to show here is an LV100 gas turbine engine. where we exploit the energy flow and entropy ideas in the feedback configuration so that we can achieve enhanced energy dissipation using this resetting mechanism that I spoke to you about. And the reason why I'm interested in that is to suppress something known in the literature as thermoacoustic combustion instabilities in variable cycle gas turbine engines. These are pressure oscillations that tend to lead to very high vibration levels, typically mechanical failure, high acoustic noise in the combustor and burn rates, and eventually component failing if you don't control it properly. So, in exploiting this unsteady coupling between the linear acoustic and the nonlinear heat release, we can potentially break this feedback loop between these pressure, wave, and velocity fluctuations and the acoustic dynamics. And what I show here is basically a hybrid architecture is extremely efficient to dissipate the energy in the combustion system, the controlled combustion system. So I'm going to take basically the energy equation, the momentum equation, and the continuity equation. I'm going to do a Galerkin expansion on these equations, and I'm going to take the first two modes. And I'm going to end up with this nonlinear state space model for my dynamical system. The variable here is not important. The first state is pressure of the first mode, pressure rate of the first mode, and then the pressure of the second mode and pressure rate of the second mode. And the alphas here and the alphas and the thetas here are nothing more than constant growth and decay constants and frequency shift constants, and gamma is the specific heats, and the parameter beta here is basically a function of the specific heats and the fundamental frequencies. The uncontrolled problem evolves into a limit cycle. You can see the limit cycle oscillations that causes this instability in the state response of the first mode and the second mode of vibration. Now, if we apply the controller through U1, U2, U3, U4 that you see here, what happens is within 0.5 seconds, actually within 1 second, you actually achieve what we call finite time stabilization, in finite time. And this is actually the physical states, which are continuous. The physical states certainly are continuous, but these are the controller states which actually reset as you go along. And if you were to plot the energy, this is what the energy looks like. This is the total energy. You can see it's decreasing. This is the interplay between the plant energy and the controller energy, and the resetting takes you here, and the next resetting actually takes you to a finite time stabilization problem. So I went through this a little bit fast because I wanted to talk more about the network problem. That's a very interesting problem, and that in some extent is much closer to thermodynamics than the previous problem. And I'm looking at multi-agent systems here, basically, and the information between agents is intermittent. It's not continuous, okay? So I'm going to look at this hybrid approach, and I'm going to use Lyapunov analysis and convergence and come up with basically protocols, control protocols, that obey conservation principles, and in particular hybrid thermodynamic control formulation principles, wherein communication events now are triggered via state-dependent resettings that are going to be completely consistent with thermodynamic principles. How do we do this? So the motivation here is that these multi-agent systems appear everywhere in engineering. You can look at them in unmanned aerial vehicles, autonomous underwater vehicles. You can look at them from a combat, surveillance, reconnaissance point of view, managing power levels and wireless network communications, air and ground transportation systems. These are very large-scale systems, swarms of air and space vehicle formations for command and control between air and space vehicles, and of course, communication networks, information flowing and routing through different networks. Now, thermodynamics can certainly be used to address this very interesting problem and perform some very interesting architectures. Now, rather than going on all these different kinds of problems, formation control, rendezvous, I'm going to concentrate on one particular problem, something called consensus or agreement between agents. That is, in another word, is state equipartitioning. Now, you can think of this as energy equipartitioning or temperature equipartitioning, but the idea is where groups of agents are required to agree on a certain quantity of interest. That quantity of interest, for example, could be a communication heading, angle, could be a shared communication frequency. And I'm going to use thermodynamics wherein I'm looking at information playing the role of energy between subsystems, or more particularly between networks. Now, even though I'm not going to talk about this in detail, the work that I have done and published basically captures different architectures and different topologies, basically switching topologies in networks. You can think of a communication link failure or communication dropouts. So the differential equation or the impulsive differential equation is no longer a differential equation, but rather a differential inclusion. You have different vector fields because of the failure of the links, and the communication dropouts change the underlying dynamics. You can look at time delays. You can actually look at functional differential equations rather than ordinary differential equations or impulsive differential equations. You can look at information asynchrony between agents. They don't have to be synchronized. All this has been addressed, but I'm not going to dwell on that because the mathematics and I just don't have enough time in half an hour to do this. But another very interesting problem is communication uncertainty, where you actually model the links between the different agents as Markov processes, and then you end up with a stochastic thermodynamic framework that allows you to do this. Now, some of the key observations between these systems is, number one, they have a continuum of equilibria, just like thermodynamics does, okay? It's a function of what initial condition you are, the initial energy, where you'll eventually converge. It's not isolated equilibria. The dynamics are captured by the exchange of information flow or energy flow, if you will. The limiting state is going to be determined by the initial conditions, and convergence is not sufficient here. You need basically something called semi-stability, which is a notion that is Lyapunov stability plus convergence. And the reason being is because convergence is not sufficient to guarantee that the small perturbations from the limited state will actually result in small transient excursions from the consensus state that you're looking for. So, and you have intermittent information within the communication events. So they're going to end up with hybrid networks. Now, hybrid systems and hybrid thermodynamics is largely not developed in the literature. And that prompted me to write a second book on the subject that actually addresses as one of its chapters, what does hybrid thermodynamics actually look like? What are the hybrid energy and entropy principles look like? What does the hybrid first and second law of thermodynamics look like? And basically, you can look at these problems from a condensed matter physics point of view, where you have critical phenomena and discontinuous phase transitions, where the thermodynamic variables actually jump. Think of latent heat release, for example. So this framework will require a hybrid foundations for thermodynamics. Now, the dynamical model is going to be impulsive differential equations. What are impulsive differential equations? Impulsive differential equations take the following structure, and I talk about that in my book on impulsive and hybrid dynamical systems. They basically have continuous time differential equations that govern the motion of the dynamical system between resetting events. They have a difference equation, the second equation, that basically tells you, that governs the way that the system states reset instantaneously when a resetting event occurs, and the resetting set that actually tells you when to reset in the state space. Now, these systems are actually quite complex, and not going into them, because you have discontinuous motion in the dynamical systems, you no longer have continuous dependence of the variables with respect to the initial conditions, and the flows are discontinuous. So they can exhibit a very rich dynamical phenomena, things like beating, where you actually encounter, you go from a resetting set to another resetting set, an infinite or a finite amount of time, deadlock, where you have no more continuity, both in the continuous and the discrete dynamics, or you might even have something called Zeno solutions, where you have an infinite number of resettings, but in finite time. So there's some very interesting behavior about these systems. So the formulation for the framework, for the network framework, looks something like this. So the state xi here, think of it as an energy state or an information state of the ith agent. The state UCI is a continuous information of the control of the ith agent, and D sub I is a discrete information of the ith agent. Then you have a bunch of local resetting sets, and I'm going to design these local resetting sets so they basically correspond to an underlying conservation law. So basically what's going to happen is I'm going to take the control inputs and the information flow functions for the continuous and the discrete dynamics to have a particular characterization that satisfy an underlying conservation principle. And by Noether's theorem, we know that for every conservation law, there exists a corresponding symmetry. And I'm going to exploit this. I'm going to take these the control law architectures, and I'm going to plug them back into my dynamical model. And this is the closed loop dynamics that I'm going to end up with. And this closed loop dynamics basically takes this form. These are what the vector fields look like. And I'm going to look at this particular resetting set. Now, this particular resetting set looks pretty complicated, but in a sense, what's going on here is you're basically looking at an index that denotes the set of all agents with information flowing out of that agent to the ith agent. This set I sub I here is the set of all other agents receiving information from the ith agent. And this I'm going to show you is actually consistent to the thermodynamic principles once I close the loop on this dynamical model. Now, so I'm back to what these the hybrid thermodynamic assumptions actually look like. They have this character that you see here. There's several assumptions, A1, A2, A3. Let's go to these assumptions in English. The first one is basically a statement that's reminiscent to the zeroth law of thermodynamics. It says basically information equality is necessary and sufficient for information equilibrium between subsystems or between agents. The second assumption is reminiscent to the second law of thermodynamics, and that basically says information flows from information-rich or more energetic agents to information-poor or less energetic agents. So in other words, heat or energy in transition must flow in the direction of lower temperatures. The third assumption tells me that actually across resetting events, I have the energy difference or the information difference is monotonic. Then I have this architecture right here that captures the interconnection between the different agents, and it's in terms of the flow functions, has a certain rank condition, has a certain symmetry condition that basically essentially says that a sequence of information connectors that connect agents I and J is actually symmetric. There's an information flow sequence between the two. So the graph is undirected and it's actually balanced. Under these assumptions, you could show that for every alpha, alpha E, where E is the ones vector, this state actually converges to this equilibrium. And this equilibrium corresponds to an equipartitioned equilibrium of consensus. In other words, it's saying that the state goes to a uniform state that is uniformly distributed over all subsystems of the multi-agent hybrid dynamical system. Now, there's something interesting that comes about here with this. You can define a entropy function for this multi-agent hybrid dynamical system, so long as there exists an S that satisfies this inequality over an entire time interval, including the resettings, then we say that this function S is an entropy function. Now, this entropy function, a necessary and sufficient condition for establishing the existence of this entropy function is this breakup into two pieces that tells you something that happens over the interval between consecutive events on the continuous dynamics and at the resetting events over an interval involving consecutive resettings. Then you could show that this form, which takes the logarithmic forms, is actually a continuously differentiable entropy function for this large-scale hybrid multi-agent dynamical system, where this bold logarithm is basically the vector logarithm. And using this fact, you could show that necessary and sufficient condition for this to be an entropy function is the derivative over the flow dynamics when it's not in the resetting set. The derivative is positive, and the difference is positive when you actually have a resetting event occurring. Now, a few observations. The resetting set basically is nothing more than the rate of change of the difference of the input and the output information flow between any pair of connected agents. When that is zero and consensus is not reached, i.e. equipartition is not reached, then reset. This entropy expression actually has an identical form to the Boltzmann entropy in statistical thermodynamics, and you could show rigorously that this entropy expression, the one that I showed, the logarithmic expression, achieves the maximum when all information states are equal. Okay, so let's take a look at an example on how this can actually be applied on an engineering problem in terms of achieving consensus. So I'm going to look at 7 aircrafts, and I'm going to look at the controlled longitudinal dynamics of motion of the 7 aircrafts. I'm going to linearize the equations of motion about a particular altitude and a particular velocity. So the dynamics look like this. The state variables for the airplane basically involve the velocity of the X and Z and Y body components. And you have the angular velocity, which is the pitch rate. And then you have the Euler angle of the airplane with respect to the axis of the reference. And then I have the control input as the elevator. So what I'm going to try to achieve here is pitch rate consensus between all 7 aircrafts. I want all 7 aircrafts to have the same pitch rate so they achieve consensus. So I'm going to design a hierarchical controller, basically one that, a 2-level controller, one that basically comes from standard linear quadratic complement control theory, and another one that basically tells me how the information flows between the different states of the controller so I can achieve pitch rate consensus. So that's higher level controller, if you will, the communication controller will directly affect the lower level controller so I can achieve pitch rate consensus in my problem. Okay, so how does this look like? So the communication topology that I have basically has this format. So the lower level controller in red will achieve command following. The higher level controller in blue achieves pitch rate consensus. And this is the communication level between the 7 aircrafts. So basically aircraft 1 communicates with 5, 5 communicates with 7, 7 communicates with 4, and so on and so forth. So I basically have the lower level controller to achieve guidance command. Then I have the higher level controller to achieve basically communication consensus. Just to get an idea, this is what it looks like. These are the simulations for the controller state. So let me see how much time I have. I think I go to 2:45. Is that correct? Or 2?
Excuse me, I see you have something like 17 minutes left, depending on how much time you want to leave for questions.
Oh, okay. So I'm actually going pretty fast. Okay, so this basically gives you the information state and the pitch rate versus time. So you could see that I'm resetting, and I actually reach an information consensus in finite time. Within the first second, actually, I reach consensus. And this is what the pitch rates look like as a function of time of all 7 aircraft. Okay, they all reach a certain pitch rate consensus as a function of time. As opposed to if you look at it from a purely continuous time architecture and not a resetting architecture, not a hybrid architecture, you still, and it's still a thermodynamic control protocol, and this is work that I did with one of my former graduate students, published back in 2008, you also actually end up getting information consensus, but in a much longer time you reach this. And this is what the pitch rates, all 7 aircraft achieve the same pitch rate, but after 8 seconds, as opposed to around 2 seconds when you do it in a hybrid fashion and you're switching between the different architectures.
Excuse me.
Yes.
Sorry. So on my schedule, I have you ending in 1 minute, actually.
Oh, okay. Okay.
Oh, my bad. I'm sorry.
Okay. So that's fine. I'm almost done. This is the one before the last slide. So,
Correct.
So this is what the entropy versus time plot looks like for the hybrid case and the continuous case. You could see that you achieve maximum entropy as you're going to this consensus state, which is a state of equipartitioned of information. Gives you much better transient performance and much faster coordination tasks in finite time, as opposed to the continuous thermodynamic protocol, which takes a little longer to get to the maximum entropy point. So in conclusion, what I talked about here is basically looked at a thermodynamic framework that captures multi-agent systems and large-scale stabilization of systems. The tools that I used are from algebraic graph theory, something called semi-stability theory, which is really Lyapunov theory, impulsive differential equations, and hybrid thermodynamics that comes out of some work that I did that was published in my recent book. Now, a lot of this has actually been extended to the case where you have communication noise between the agents, where you have errors in the information transfers or attenuations, where now you can capture that using exogenous stochastic disturbances by modeling the interconnections of the information between the agents by Markov processes. Rather than looking at single trajectories, then you look at basically ensemble trajectories, and you look at different sample spaces reaching consensus of the system. And that should pretty much bring me to the exactly allotted time that I had. Is that correct?
Yes, and there's of video that I will play for 30 minutes. And then after the video, there will be additional 15 minutes for Q&A for the plenary and keynote speakers.
Okay, thank you.
Thank you very much, Wassim. Apologize for the mix-up. I set my
That's okay.
stopwatch wrong.
I was wondering that I had a little bit more.
Well, we had 45 minutes for the first speaker, and so I just pressed the button again, and
Okay.
that's why I got it wrong. Yeah.
Thank you. Thank you.